Okay. Good morning. Let's get started. I heard that you had some problems with the rail cycle analysis of the two aircraft that I asked you to do. The reason might be underestimation of the efficiencies and the overestimation of the pressure drops and things like that. Now, as you can imagine, data is not available on those things. That's one of the reasons it's difficult to do real cycle analysis. You have to know the component efficiencies, accurately. But since we don't know that, I gave you what I thought was appropriate for engines of that era. I might have underestimated the efficiencies. So I haven't had a chance to run those things myself. I tried to do it this morning, but ran out of time. So what I will do is extend the deadline to Thursday. Okay. And today I will actually work on the problem as well as the MATLAB code to do cycle analysis of turbojets and turbofans. So I can provide you that MATLAB code if you so desire. Yeah?
So I researched the turbine temperature, found it was a bit higher than mine. And increasing that helped?
Yeah, that helps. That helps. 1,000 degrees Kelvin was probably an underestimate for SU-25 because 1,000 degrees Kelvin was appropriate to sort of a Whittle engine type at that era. So maybe 1,200 might be appropriate. So play around with that, and if you still need help, let me know. Okay. Meanwhile, I'll work out the problem myself and try to see what is appropriate to do. Yeah, increasing the temperature would increase the performance significantly. And the efficiencies, maybe bumped up a little bit. So give it a try. Okay, I was saying people are having problems with the real cycle analysis. So the problem might have been underestimation of the TT4. So please increase that. Now the code I have, the MATLAB code, does both ideal and real cycle analysis given the various inputs. So I will make it available on D2L sometime today, if not tomorrow morning. So all you have to do is put in your inputs, and it should come out with the answers. Okay. Now, I was also planning to give you a homework, send a homework today on performance analysis. Okay. Now, once again, I don't want you folks get bogged down because the performance analysis, especially for turbofans, involves iteration and things like that. So unless you have the MATLAB code and have debugged it and so on, it may take a lot more time on your part than optimum, so to say. So I will also provide a MATLAB code for that, and all you have to do is input your variables and run it. Okay. Now, I have a Fortran code that does that, but I don't have my license. Fortran license has expired. Since I keep asking you guys to do everything in MATLAB, I might as well go ahead and convert that into a MATLAB. And once I convert it, then it should be straightforward for you guys to use it. So be patient. I'll have these things sorted out soon. Yes?
What's the word on the midterm? Are we?
Sometime in the next week or two. Okay. Now the midterm for this class is usually a take-home one. So essentially, I will ask you to go ahead and look at the performance of your the engine, one engine on the aircraft that you have selected. Okay. So don't worry too much about it. Should be fairly straightforward now that we have gone through all the cycle analysis and things like that. Okay. Now, as far as news is concerned, there's not much happening in the aircraft arena, except that both the Airbus and Boeing competition is quite stiff. They are arch rivals, and when A320 new engine option was launched by Airbus, 2-3 years ago, something like that, the launch customer was Qatar Airways. Okay. The CEO of that airline is a chap by name Al Bakr. Okay. And that particular gentleman is very, very particular about the aircraft he receives, and he has in fact refused to take charge of aircraft because things like interiors now is not been done right and things like that. So he's very, very picky. Now he had ordered quite a few A320neos as a launch customer. Now when you are a launch customer, usually you get a break in pricing. So anyway, it so happens that the A320neo is having problems because of the engine. The aircraft itself is fine, but essentially Airbus is building gliders. They're building these A320neos without any engines and parking them outside their factory on the tarmac. Okay. Simply because the Pratt & Whitney has been unable to deliver the engines. The thing that caused all these problems is the so-called engine bow, the shaft bow. In order to, this is a teaching moment. In order to squeeze as much efficiency as possible out of the compressors and turbines, it is essential to prevent what is known as tip leakage. Okay? If there is a clearance between the blades and the casing, then the air tends to flow around the tip. That's called tip leakage. Okay? Now, this tip leakage must be avoided at all costs. So there are varieties of things that engine manufacturers do to minimize tip leakage. One of those is actually have the blades, hardened blades, actually on the casing have soft abradable material, so that the blades abrade it, and therefore the clearance can be very small. The whole point is, if the blade touches the casing and gets stuck, of course it can have an engine failure. So you cannot permit that. But at the same time, you can't have too much clearance. That causes tip leakage and therefore inefficiencies in the performance of the compressor and the turbines. So especially the compressor. Now, as you can imagine, when you're talking about very small clearances of the order of the thousandth of an inch or something like that, any distortion of the casing or the deflection of the shaft can cause the blades to touch the casing. So The problem Pratt & Whitney is having with the A320 engines is that after the engine has been operating for some time, okay, if they shut down the engine or during, after landing, right, then the lower parts cool quickly, but the upper parts of the engine don't cool that quickly. So there is a distortion, very small distortion that can make the blades touch the casing. In order to prevent that, they essentially say that you have to allow a certain amount of time to pass when everything cools down, and then you can start. Now, as you can imagine, if that time is too long, then it impacts the turnaround time of the aircraft. So Al-Bakr refused to accept the A320 neos with this problem. Other airlines accepted it. They don't like the increased turnaround time. Optimally, the turnaround time for these narrow-body airliners has to be around 30 minutes. That's about optimum. Anything that extends to 60 minutes or something like that, they're losing money. So Pratt & Whitney, because of the secrecy involved in all these things, we don't know exactly what causes that problem. They did not have a similar problem on the C-series aircraft from Canadian manufacturer Bombardier. Now, the one thought is that the way the engines are mounted on the wing, okay, whether it is the fan casing that is attached, or the body of it and things like that. They had a problem with this mounting because the casing has to remain circular. If it deforms, gets an elliptical shape, and then of course once again blades can touch the casing. A long time ago they discovered that instead of having a single mount, they had to have a sort of a Y mount to prevent that distortion of the casing. Now, so that suggests that maybe so the way they attach the engine to the aircraft may be a problem, okay, because this didn't show up with the Bombardier engines, C-series aircraft engines, but shows up with A320. A320, the mounting is different between the two. So that's one possibility. Other possibility is, some mechanical thing to do with the bearings, whatnot. So as a result, Airbus has not been able to deliver the aircraft as promised. And for airlines which plan far ahead, this throws a monkey wrench into their operations. And so Al-Bakr essentially refused it. Not only that, he actually went and ordered the 737 MAX aircraft. Okay? So they made a big deal out of it at a press conference a couple of days ago, where he actually said Boeing builds better aircraft than Airbus. I don't think Airbus agrees with that, and most people don't agree with that. They make a comparable aircraft. Airbus is having a lot of problems, supplier issues. So, once again, Pratt & Whitney, once again, a supplier issue. They cannot make everything that the engine needs themselves. So they have to outsource many things. And when you have a huge order backlog, you have to increase the production rate. Now, the main problem is the engine manufacturer can do that, relatively easily, but the suppliers cannot. So that becomes an issue, okay? Especially if the supplier quality is not good, then it throws a monkey wrench into the works. For example, A350 aircraft has also been delayed quite a bit because the suppliers cannot supply the interior. They are having quality issues with the interior supplied by, one of the suppliers, and unfortunately they are stuck with that particular supplier. So they had to work with them to take care of the quality issues, and that produces, delays in the delivery of the aircraft, and that's not good at all. It's just airlines don't like it, and the airframers get a bad reputation. So anyway, there is no news on what Boeing will do to challenge Airbus on the A321 type aircraft. That is between the narrow bodies and the wide bodies. There is a gap, and that gap has been filled by Airbus with their A321s, and Boeing has to do something or concede the market. And no word on what they're going to do. If they are going to launch a clean sheet design now, it will be another at least 6 years before it enters the market. Now, the engine for that is not clear. Will they use a version of existing engines or demand from the engine makers that they make further improvements in TSFC and things like that? So that's not clear. So this is a difficult gap to fill, because the number of passengers is, say 220, 230, something like that, between a typical narrow body passenger capacity of 180 and a typical wide body capacity of about 250 plus. So in between this, how do you build an aircraft? The question is, does it have to be a narrow body aircraft or a wide body aircraft? Because if you make it a narrow body aircraft, it will be, it will become too long, okay? And therefore the embarkation, disembarkation times are going to be much larger because of a single aisle. Okay? As you increase the number of passengers, twin aisles are better for loading and unloading the aircraft with passengers. So, but if you go to twin aisles for that range, the drag increases because the fuselage size has to increase. So the drag increases, and those the fuel economy suffers. On the other hand, if you go for a single aisle aircraft, the turnaround time increases, and that is not good. So the Boeing is faced with the task of building an aircraft, perhaps a single aisle, or perhaps twin aisle, but with the economy of the single aisle, fuel economy, and that's where it is stuck. So I'm quite sure Boeing engineers are working very hard to solve that problem. So we'll see what they come up with. Otherwise, they lose that market. All right. So far we have looked at how to assess the overall performance of the engine. Now it is time to look at individual components. What affects their performance, how they are designed, etc., etc. Now, we will come back to the rotating components later, meaning the compressor and the turbine. Okay. But before we do that, it is logical to talk about non-rotating components like inlets, nozzles, and combustors. Okay. So we'll start with the inlets. Okay. Now, the nozzles are fairly straightforward to design, especially for civilian aircraft. Military aircraft, of course, have to have convergent, divergent nozzles and some way to change the exit area as well as the throat area. Okay. Since military fighters invariably have an afterburner. If you light the afterburner, then the mass flow rate doesn't change much, but because of the release of heat, obviously the temperature increases and therefore density comes down. Okay? Which means for the same mass flow rate to be passed through, the throat area has to increase. So you have to have some way of changing the throat area for a nozzle. Okay? And the exit area, of course, you have to have a convergent divergent nozzle to accelerate the gases beyond Mach number equal to 1. Remember, the throat Mach number is equal to 1. So if you want to have good performance nozzle, you have to have a divergent portion. So you are now faced with the task of having a nozzle that is mechanically complex, meaning you have to have some way of changing the throat area and the exit area. Okay? So apart from that complexity, the nozzle operation and design are usually quite straightforward. Okay? Simply because there are no rotating components in there, and therefore it is relatively easy to cool the nozzle, and if you have an afterburner. So we'll talk about those a little bit later, but let's look at inlets. Okay. Now the inlets have a task of having to deliver air to the engine at the proper Mach number without any distortion. Okay? That is the most important function of the inlet. Okay? Deliver the required mass flow rate at the required Mach number and do it with minimum distortion. That is simply because at least the current engines don't tolerate the flow distortion much. And it is quite possible that if the distortion is excessive, the compressor can stall or surge. Okay. And that is, of course, not allowable. And all this has to be done with minimum loss of stagnation pressure. Okay. So inlet design has to be done rather carefully, and one has to make a distinction between whether the inlets are for subsonic aircraft or supersonic aircraft. Okay. For subsonic aircraft, the inlets are fairly straightforward. There are issues involved, such as minimizing the additional drag involved in mounting the engine on the aircraft. Whatever that installation is, under the wing, in the rear, above the wing, whatever the case may be, the installation produces additional drag. Okay. The engine has to be enclosed in a nacelle, and of course the nacelle itself will produce a drag, both a pressure drag as well as a skin friction drag over the nacelle. Okay. That is one. Secondly, under most conditions, I should say, there is also what is known as an additive drag, because the streamlines coming into the engine are not straight. Okay. So essentially, subsonic inlet designs try to minimize the so-called additive drag due to the fact that the stream tube is not straight, and the nacelle drag by appropriate design of the nacelle. Okay. The flow usually over the nacelle accelerates, since the cruise Mach number is 0.8 plus, typically 0.85, Boeing 747. The flow over the nacelle can accelerate locally to slightly beyond Mach number 1. Okay. When that happens, the deceleration on the back side at the rear of the nacelle usually involves shock waves. Shock waves mean, of course, additional losses and therefore increased drag. So one has to make sure that the shock wave that terminates the supersonic region above the nacelle is as weak as possible. And that in turn limits what diameter of the nozzle you can select. Okay. That is for subsonic inlets. Okay. Actually, the subsonic inlets are relatively straightforward to design compared to the supersonic inlets, because as you can imagine, supersonic inlets have to decelerate the flow for from supersonic Mach numbers to subsonic Mach numbers. Okay. The engine typically likes air at maybe Mach number 0.6, something like that, around that value. So if you're cruising at Mach 2.5, you have to decelerate the flow from that Mach number to 0.6, and of course the only way to do it is through shock waves. So shock waves are unavoidable for supersonic inlets. Okay. The trick is to try and minimize the stagnation pressure losses due to the presence of shock waves in supersonic inlets. Okay. So that we will talk about. So that is a major difference between subsonic inlets and supersonic inlets. Now, the let's talk about subsonic inlets. Okay. Now, looks like the most favored configuration as far as engine installation is concerned is underneath the wing. Okay. The advantages of having the engines hung under the wings is simply due to the fact that the engines, weigh quite a bit. Okay. And in terms of a few metric tons, depends on the size of the engine. So mounting the engines on the wing essentially counteracts the lift force during cruise, which means the net bending moment at the wing root is reduced because of the weight of the engine. So that is a very important consideration, because that in turn reduces the weight of the wing that needs to be designed, and that is of course improves the fuel efficiency and things like that. But mounting the engines under the wing changes the flow around the wing. Okay. There are other practical considerations when it comes to the engine installation, because the engine installation should not adversely affect, say, the airport operations. Okay, because as you can imagine, the walkways and things like that airports are equipped with, they have a restricted range of operation, and therefore, if you try to hang too large an engine underneath the wing, the operations might get affected. For example, when A380 was designed and put into operation, they had to have design special gates because it's a double-decker. So to accommodate quick passenger embarkation, disembarkation, the gates had to be specifically designed for the A380. Okay. Now, one of the important considerations, of course, is the ground clearance, okay, and the length of the landing gear. Okay. the ground clearance required 2 points. One is ingestion of foreign objects. So FOD is an important consideration. Okay, too close to the ground, there's a danger of ingesting objects that can cause damage. Okay. The second one is if the nose gear fails, the certification requires that suppose the nose gear has collapsed for some reason, and you have engines hung underneath the wing. The certification requires that with the nose gear collapse, there should still be some clearance between the engine and the runway surface, so that this won't be torn off. Okay, that's a very important consideration. Okay, all this means, of course, the landing gear has to be appropriately, the length has to be appropriately designed, and it can't be too long. Okay, so there are many such considerations that come into play. Okay, precisely where one should, how close to the wing, and how far ahead the engine has to be placed. Okay, is determined by very careful wind tunnel measurements and CFD simulations. Okay, now we want to hang the engines far upstream of the leading edge. Okay. The reason for that, of course, is any uncontained failure should not cause damage to vital parts, in the wing, including the tanks, and cause a hull loss. So invariably, the underwing installations, the engine protrudes quite a bit ahead of the leading edge. Okay. Now, this is advantageous in the sense that now the engine is essentially ingesting fairly undisturbed air. Okay. Although, if you notice carefully, the inlet plane of the nacelle is tilted a little bit, about 3-4 degrees. Now that happens because the lift on the wing produces an updraft ahead of the wing and a downdraft behind the wing. And the updraft essentially changes the angle, and therefore, you have to accommodate for that. So that angle is about 4 degrees. You can easily calculate what that is. Okay. Normally, these engines are hung quite a bit below the wing. Okay. For example, look at the 747 design. That is the wing, and the engine is significantly below. Okay. On the other hand, if you look at a Boeing 737, for example, the engine is almost, the top surface is almost level with the leading edge of the wing. That is simply because the 1950s design of the landing gear accommodated only a small diameter engines, because 737 was essentially designed at that time. Turbojets are very low bypass ratio turbofans were the engines that drove those aircraft in those days, and those had small, they were more like cigar-shaped engines. Okay, and therefore the design was such that the landing gear didn't have to be too long. Now you take that engine, take that design, landing gear design, and the fuselage design. And then you want to hang a large diameter fan underneath. What do? You just don't have enough clearance if you hang it well below the wing. So the Boeing engineers worked very hard to figure out how to mount that engine almost, level with the wing, still not cause too much additional drag. Okay. Now, A320 design was, on the other hand, was in the 1980s. Okay, and therefore, by that time, moderate bypass ratio engines were the norm, and therefore they designed it with appropriate, landing gear length and stuff like that. So now they can accommodate, 81-inch fans. Remember, the Nozzle diameter is going to be significantly larger than the fan diameter. Okay, 81-inch fan means, let's say, 15% more, anywhere between 10 to 20% more diameter for the nacelle. So that's once again something working in favor of Airbus. Okay. Anyway, this wing nacelle interaction is quite important, and the configuration has to be chosen very carefully. Now, remember, it is the upper surface of the wing that usually produces a significant part of the lift. So you want to keep the upper surface as undisturbed as possible. This is one of the reasons that you don't see over the wing engine installations. Okay. Now, over the wing installations would produce the same load relief as under the wing engine installation, but over the wing it tends to disturb the flow and therefore affect the lift to drag ratio, and therefore until very recently, such mounting was not favored. Okay. But I think the Japanese business jet, I forget the exact name of the jet, was designed with engines over the wing, which demonstrated that by careful attention given to the location of the engine with respect to the leading edge, it is installed fairly at large distance from the leading edge. They showed that yes, it could be done. So some of the future designs may have engines over the wing. Okay. Now, the additional advantage, of course, is if you mount the engines over the wing, then the wing tends to decrease the noise radiated downward by the engine, and this helps, of course, during takeoff and conditions where the noise may be a problem. So noise shielding by the wing is an additional factor that favors above the wing installations. But so far, we haven't seen over the wing installations for this, the usual 100 plus passenger aircraft. So, both the aircraft and engine manufacturers are highly conservative because a mistake, mistakes can be costly. So they usually do evolutionary changes, slight things, changes here and there. They don't want to undertake radical changes, such as shifting the engines from under wing to over the wing. So that is something they won't do unless they're absolutely convinced that that is beneficial. Okay. Boeing's gamble in doing composite fuselages, barrel type, composite fuselages was a significant problem because the learning curve was steep, and that contributed to the delay of the delay into service of the aircraft. So usually both engine makers and aircraft makers are very reluctant to make radical changes in the design. Okay. For example, that's one of the reasons geared turbofan has, the concept has been around for a long, long time, and everyone knew that introducing a gear between the fan and the low pressure spool would be quite advantageous, but took a lot of time and money to make sure that that radical change in the engine architecture still was safe in terms of the acceptance, maintainability, and things like that. So anyway, here's the typical flow with the engine mounted underneath the wing, and you can see the flow between the wing and the nacelle is affected. Okay. The flow is significantly affected by the presence of the wing. Okay. Over the wing, of course, is usually a small supersonic flow region terminated by a weak shock wave. Next time you travel, look, if you have a seat over the wing, just look over. Under certain conditions, you could see the weak shock wave on the wing. Anyway. There are two operating conditions that are critical to the design of subsonic inlets. One is takeoff. Okay. At the end of the runway, the engine is in full throttle, and of course the aircraft is not moving. Okay. In that particular situation, you have now, there is no motion, Mach number is 0, and therefore the flow that comes into the engine, the stream tubes look like this. It's like a sink flow. Okay, so the flow coming in has to turn around, and if you don't design it properly, it can separate. Okay, so this is one reason that if you look at the subsonic aircraft nacelles, you have a significant laminar shape with small curvature, so as to accommodate the flow coming in without separation. On the other hand, if you made the nacelle very sharp, for example, like that, the flow coming in could separate. Okay. So that is one operating condition that needs to be taken into account. Okay. Now, another one is takeoff under crosswind conditions. So during takeoff, of course, we have air coming in, getting accelerated into the engine. Okay. But if there is a substantial crosswind, across the runway, Now that once again can cause problems with the flow. Separation is a possibility. So that has to be taken into account. If you ever have a chance, take a look at some YouTube videos of aircraft landing under very strong crosswind conditions. I mean, they're crabbing, really. You have to see that. That's actually fascinating to watch how they accomplish landing in such high crosswind conditions. Now, that speaks to the pilot skill. But as far as the design is concerned, after you have built your aircraft, during the certification process, it is usually taken to a runway somewhere in the world where the crosswinds are really quite strong. So it has to be proven. The proper functioning of the engines have to be proven under strong crosswind conditions. Okay. Now, before that, of course, static testing involves, once again, strong crosswind. So there are huge fans generating, crosswind, and the engine is, tested under those conditions, data collected, and then, of course, when it's mounted to the engine, the whole aircraft goes through the certification process. Once again, they go to a place where which is well known for strong crosswinds, and they test the aircraft and take, additional data for certification purposes. Okay. It's a long process, building an aircraft and getting it certificated is a long, long process, both for the engine makers as well as the airframe makers. Because the engine makers, of course, have to do static tests on their, static test stands under varieties of conditions. And then when all that is proven satisfactory, then they mount the engine on a test aircraft and then collect data under realistic flight conditions. And after that is done, the engines are supplied to the airframer, they mount it on the engine, and then they put the aircraft through, variety of certification, tests required. Okay. Long, long process. Usually, roughly about half a dozen engines participate in the certification process. Okay. And usually 3 to 4, maybe 5 aircraft, depending on how quick the airframer wants the certificate, participate in the certification process. Yeah. One more thing to note is in modern aircraft design, the fan is mounted well to the rear of the inlet. Okay. This is simply to allow for the possibility of putting acoustic liners in the inlet so that they absorb some of the noise being radiated by the fan forward. Okay. Secondly, you can also install heaters there to prevent ice buildup. Okay. Now, the problem with ice in inlets is that if you allow it to build up, thick chunks of it may break apart and, of course, can be ingested into the engine and damage it. So you have to have provision for heating the inlet and prevent buildup of ice. Okay. So that has to be allowed for, and of course that is usually done either through using air from the compressor, hot air from the compressor for de-icing purposes, or that's the usual way that's done. Anyway, we talk about that. Let's talk about the additive drag. Okay. Now, one of the important things that you must understand is the isentropic flow inside a duct. Okay. Now, there is a section on that in my appendix, so take a look at that. But the most important thing is this mass flow parameter can be defined as the mass flow rate through the duct times the square root of the stagnation temperature divided by the area of the duct times the stagnation pressure. If you define it that way, the mass flow parameter becomes a function of only the Mach number. Okay. Now, since in an isentropic flow, both the stagnation pressure and the stagnation temperature, both of them are constant because there are no losses, entropy is constant. If you apply the conservation of mass, you can show that the ratio of the area ratio, say at two sections of the duct, essentially depend on the two Mach numbers. Okay. So these two are important. Let's see if I have it here. No. I don't have it, although I say I do. It's not right. Okay. Let's do this. So this figure shows the mass flow parameter times square root of the gas constant. Of course, the gas constant is the same for air, doesn't change. So that, as a function of Mach number, the mass flow parameter is the maximum at the throat, where Mach number is equal to 1. Okay. And if you take the area at any section divided by the area at the throat, that area ratio is once again a function of only the Mach number and of course gamma, but if you assume gamma is constant, then it's only a function of the Mach number, and that area ratio is of course equal to 1 at the throat. And for subsonic flow, it doesn't matter whether it's subsonic or supersonic, anything other than Mach number 1, the area is larger. So this is very important to realize. Okay. Take a look at that section, read that, because we'll be using that quite a bit. So coming back to this, so this is essentially a repetition of what that is. Okay. Now, how does the additive drag come about? Well, the additive drag comes about because unless this Mach number is equal to the Mach number here, the stream tubes are not straight. Okay. In supersonic inlets, once again, the stream tube will be straight because until the flow hits the inlet, it doesn't know the presence of the inlet, and therefore stream tubes are straight. But for subsonic inlets, there is upstream influence, and unless this Mach number is equal to this Mach number, the stream tube will not be straight, and therefore the pressure acting on the stream tube, the component of that in the direction, in the axial direction, produces a drag. Okay. If the stream tube is like this, the pressure outside is higher than the pressure inside, and therefore that causes a drag. On the other hand, if the flow has to be accelerated, in other words, this Mach number is less than this Mach number, then the stream tubes will be curved in the other direction. The pressure will be lower on the outside than inside. Once again, it acts to produce a drag. So this is called additive drag. Okay, it is fairly straightforward to calculate. A simple integration, for example. So if you take the capture stream tube and use the conservation of momentum and integrate the pressure between the areas A0 and A1, that is the inlet area and the area of the area far upstream, then you can show that the additive drag, of course you normalize it with the ambient pressure and the inlet area, looks like this. Okay, and using relationships for the temperature and pressure ratio for an isentropic flow, you can derive an expression for the additive drag, which is a function of the two Mach numbers, the upstream Mach number m0, undisturbed flow, and the Mach number m1 at the inlet. So these are the two Mach numbers that govern what the additive drag is, and you can plot it actually. So the additive drag normalized suitably looks like this. For example, if you're traveling at Mach number 0.4, okay, and the Mach number at the inlet is also 0.4, there is no additive drag. In other words, if m0 is equal to m1, there is no additive drag. Just simply because m0 is not equal to m1, in most cases, you have additive drag. As I said, let's say we need to bring down the Mach numbers to say 0.6, okay, and then you're traveling at say 0.8, okay, then you have this additive drag being produced, and that has to be taken into account, obviously. Anyway, the derivation, I don't have to go through the derivation. It's simple, fairly straightforward, making use of the isentropic flow relationships I mentioned earlier. If during cruise the Mach number, for example, comes down, if an engine fails during cruise, you have to essentially slow down the aircraft. Okay. And in that case, let's say M1 has to be 0.4, then the normalized value is 0.1, and therefore the additive drag can be quite high. Okay. So this is, once again, has to be taken into account. One engine out, one engine inoperative cruise conditions. Additive drag is especially high at the end of the takeoff run, because takeoff usually Mach number is about 0.2, and of course we need 0.7, let's say, at the inlet, and so that is quite a bit of a change in Mach number. So if you go and look at, let's say M1, we have say 0.7, that curve is going to fall between these two. And if M0 is 0.2, like during takeoff, this normalized drag can be as high as 0.1. P naught times A1 is quite significant, and therefore the drag can be quite high, 13,000 newtons. That's something you cannot ignore. But in most cases, the additive drag is compensated to varying degrees by the so-called lip suction force. Okay? As the flow accelerates around the outside of the nacelle, the pressure there comes down. Okay? And the component of the pressure acting on the surface in the direction of flight produces a lip thrust. So this lip suction force produces a lip thrust that tends to counteract the additive drag. Okay. Once again, these things are important in the nacelle design. Now, the portion of the inlet between the inlet plane and the fan face is essentially a diffuser. Okay. So by shaping it appropriately, you can decelerate the flow, making sure that the boundary layer on the inside surface of the nacelle does not separate. Okay. So you need to keep the divergence angle of this diffuser section below about 3 degrees. Okay. What I'm talking about is this divergence angle. This angle here. Because this is a diffuser section, the area has to increase, and in order to keep the boundary layer from separation, you have to keep that angle below a certain value. That's the angle is usually about 3 degrees. So the length has to be, the length of that inlet section between the lip and the fan face has to be appropriately chosen. And of course, that section can be used for acoustic liners and heaters to de-ice the nacelle. Now, if you look at this sketch, this point is known as the highlight. So this is where A1 is measured. We keep talking about A1, the lip of the inlet. Now, obviously, there's a throat, and then, of course, a diffuser. Okay. Now, this is subsonic flow. Okay. The flow coming in is subsonic. But if the throat area is sufficiently small, then you can easily reach Mach number of 1. We don't want that, because once you reach Mach number 1, the flow accelerates further, and the diffuser section becomes supersonic, and of course has to be terminated by a shock wave. So that's not convenient. So the maximum Mach number at the throat section must be kept less than 1. Okay. But the velocity profile is going to look like this. In other words, there is some distortion of the flow, and therefore the average Mach number has to be kept less than about 0.75, so that the maximum one is still less than 1. Okay. So that essentially decides what the throat Mach number has to be. Now, it is usual to design the nacelle such that the same nacelle can be used for future versions of the engine which may have a higher thrust. The way this thing works is the engine manufacturers makes an engine for a particular aircraft, but he builds in some cushion in there so that the thrust can be increased suitably by a few percent as time goes on to accommodate, for example, increases in the takeoff mass of the aircraft, accommodating more passengers or whatever. The airframe designers would always like to improve the capability of their aircraft. Remember, the initial design is always conservative. Okay, so they design the aircraft with quite a liberal allowance in terms of masses and things like that. But once the aircraft begins to operate, the data collected may suggest that you can decrease the masses or increase the takeoff mass, for example, without any adverse effects. But usually the increase in takeoff mass requires an increased thrust of the engine to maintain the takeoff performance of the aircraft, which means the engine maker has to produce a version for the later versions of the aircraft that can provide an increase in thrust by whatever percentage. And usually you don't want to redesign the nacelle. Remember, the engine is also the same, except that maybe they will push up the TT4, for example, by suitable modifications of the engine to produce a higher thrust. So the engine is the same. The nacelle now has to accommodate, say, increased mass flow rate, which means that you can easily violate this condition if you don't design your nacelle appropriately. So usually the initial design of the nacelle is conservative, so that future versions can accommodate the changes required. This is what I was talking about. The current tendency is to go for slim nacelles because already the size of the engines is large diameter fan engines. The size is quite large, and if you do a conventional nacelle, then the outer nacelle diameter would be too high. So a slim design is preferred as much as possible. Okay. But the slim design has the disadvantage of potential separation during takeoff and also crosswind conditions. The slim design tends to reduce the acceleration of the flow going around the nacelle. Therefore, the shock wave terminating the supersonic region will be fairly weak, so additional drag is less. Whereas in this design, the separation is prevented, but you may have additional drag due to presence of a stronger shock wave on the outside. So once again, it's a compromise. Okay. Now, the drag on the outside of the nacelle is not only pressure drag, okay, where things like the presence of shock waves come in, but it's also skin friction drag. Okay. Let's assume that the shock wave on the outside of the nacelle is sufficiently weak so that it does not separate the boundary layer. Okay. But the boundary layer, if the boundary layer is turbulent, then the skin friction on the outside of the nozzle will be large. So the current trend is to try and postpone the transition from laminar to turbulent flow in the boundary layer outside the nozzle. So let's say This is conventional design. The boundary layer develops here, and initially it is laminar, and then it becomes turbulent. Okay, so this is the transition point. Now, the skin friction, if the boundary layer is turbulent, is higher than if it stays laminar. So the current trend in designing nacelles is to the so-called laminar flow nacelles is to postpone by suitably designing the shape of this nacelle so that the boundary layer stays laminar for a longer period before it becomes turbulent. So let's say we postpone transition from this point to this point. That means the boundary layer flow is laminar for longer, and therefore the drag on the nacelle is reduced. 787, Boeing 787, is designed with a laminar flow nacelle. I think I did some calculations and showed that the drag was reduced by a few hundred newtons. Okay. This is what the airframers are doing, trying to squeeze out the drag as much as possible by doing things like that, because drag reduction shows up in terms of reduced fuel consumption. That's as far as, oh, I'm already over time. That is pretty much, I wanted to give you a quiz. I ran out of time. So I will give you the quiz Thursday, okay? I just talked too much, okay? So, and this is this sort of stuff that we have done, cycle analysis and things like that. So I will do that next class. That's as much as we can need to talk about subsonic inlets. Relatively straightforward, but optimization of the inlet requires careful attention to the nacelle to minimize the additional drag that the nacelle produces. And that's about it. But supersonic inlets will take up on Thursday. Meanwhile, I will go ahead and try to get that MATLAB conversion of Fortran to MATLAB done today, and I will assign the next homework on the performance analysis. Okay? So anyway, remember the due date is postponed to Thursday, and meanwhile I will work out and see what is appropriate in terms of the temperatures and things like that. Okay? All right. Thank you.